Okay, let's try to discuss the last theorem in this section, Arcela-Ascoli theorem. So, Arcela-Ascoli theorem. So before we present and prove this theorem, we need some results. So first, let's see. Let Xn Dn be a metric space. For each n greater than or equal to 1. So we have a sequence of metric spaces. And let X be the product, direct product of Xn, and from 1 to infinity. Okay, be their Cartesian product. Okay, and that is X is, okay, let me write here. X is the set of all psi, where psi is x1, x2, x infinity. Here, Xn belongs to capital Xn for each n greater than or equal to 1. It's just infinite Cartesian product. Okay, so for this psi, this is a sequence of Xn, and either be a sequence of another sequence Yn in this X. We can define the distance between psi and eta to be, and from 1 to infinity, 1/2 to nth power dn xn yn over 1 plus the distance between xn and yn. Alright, so we know that if we have just Cartesian product of two metric spaces, we can define the metric in a different way. But if we have a sequence, a different simple way, right? If you have a r cross r, the distance of x1, y1, x2, y2, we can define it to be the by the Pythagorean theorem, x2 minus x1 square, y2 minus y1 square, right? But when we have those infinite sum, then this sum may not make sense. So we use this special setting. Okay, with this special definition, let's see the proposition 1.18. Whenever you have finite, so here is R2, R3, R4, Rn. Rn, we have the similar definition, but if we have R infinity, this is more or less like R infinity, we have to use some trick to define the metric, right? Okay, so what is the proposition 1.18? So we have this Cartesian product xn from 1 to infinity with this defined D, where D is defined above. Okay, this is a metric space. Okay, and also if psi n, a sequence in this Cartesian product, which we write like xk sub n from 1 to infinity. Each k, psi 1, psi 2, each k, it represents a sequence, right? If psi k is in x-axis in the xn, and from 1 to infinity, then psi k approaches psi, which we call it xn, if and only if xkn approaches xn for each n. Also, if each xn dn is a compact, then this Cartesian product is compact. Okay? So each x is compact. The Cartesian product of compact space is compact. Okay, so that's the proposition. So the Cartesian product of metric space is metric, and the convergence is component-wise convergence. So if for each coordinate component, each coordinate component converge to xn, then the new element sequence xn will be the limit of this psi k. It's component-wise convergence, and plus compactness implies compactness. Okay, so the first part, we have to show this is a metric space. To show metric space, basically we show D is a metric function. So we need to show that D is a metric function. Metric function. What is a metric function? Let's in the textbook it is left as an exercise. Let's prove it. What is a metric function? Metric function is positive definite, non-negative, equal to 0 if and only if you have two same points, and symmetric. And the essential thing is a triangle inequality. Okay, so usually the first and second conditions can be verified easily or trivially. We just literally verify the third condition, the triangle inequality for this D. Actually, we do not directly verify D satisfy the triangle inequality. We verify that here it suffices to show that this function d over dn over 1 plus dn is a metric. Is a metric on Xn. If each component is a metric, then you add them together, it also satisfies the triangle inequality. So we're going to show this satisfies the triangle inequality. Well, how do we show it satisfies the triangle inequality? So we get x, y, z in Xn. Okay, we know that dxy, the distance, yes, is less than or equal to dn of xz plus dn of zy, not plus zy. This is a triangle inequality from the dn. And you examine this function x plus x over 1 plus x, it is equal to 1 minus 1 over 1 plus x. 1 minus 1 over 1 plus x is increasing. This is an increasing function. Okay, xn is bigger, you subtract the smaller number, so it's increasing. When you have an increasing function, we have that the dnxy over 1 plus dnxy less than or equal to dnxz plus dnzy over 1 plus dnxz plus dnzy, not plus the xz, yeah. Okay, so this result comes from the increasing property of this function 1 over 1 plus x. All right, so now it suffices to show that this function dnxz plus dnzy over 1 plus dnxz plus dnzy less than or equal to these two. When you substitute dnxz in this function, so it's a dnxz over 1 plus dnxz plus dnzy over 1 plus dnzy. Okay, so we are going to show this. To show this one, I don't want to copy all these stuffs, so it's equivalent to show that a plus b over 1 plus a plus b is less than or equal to a over 1 plus a plus b over 1 plus b. You're going to show this inequality. Well, this inequality, just brutally do the subtraction. You use the right side to subtract the left side, and remember this is a, b, non-zero, non-negative. So you just brutally compute this. You will verify it is correct. It is correct. By doing subtraction, we can prove the above inequality. I really did this. You try to do it. It's not difficult. Just do the right side minus left side and find the common denominator and compute the numerator. You will see what it is. Okay? Okay, so by doing subtraction, we prove the above inequality. Then we get the dn over 1 plus dn is a metric. And d, which is a sigma 1/2 to nth power dn over 1 plus dn n from 1 to infinity is also a metric. It's also a metric. Okay? So this is the verification why this Cartesian product is a metric space. All right. Okay, now let's examine this process. Let's check what we have. Actually, in this proof, what we use some let's leave this a proposition. Just study this proof. In this proof, we use the following condition. Dn is a metric. Here. Dn is a metric. We use it here. And second, this function, x over 1 plus x, is increasing. Here. Okay? Of course, and let's call it fx. And f0 is 0. So it's also important. f0 has to be 0. So Dn is a metric. A function x over 1 plus x is increasing, f0 is 0. And then another condition is this condition. This condition, if we summarize it, make it abstract, third condition, fa plus b is less than or equal to fa plus fb. It's called a subadditive. Subadditive. It's not additive. Additive, it is equal. It's less than or equal. We call it a subadditive. Whenever you have these conditions, so we have a little remark. D is a metric. F is increasing subadditive, and f0 is equal to 0, then f compose D, the composite function, is also a metric. So this is actually a general result. You can do whatever composition between a matrix function with a function with these properties, increasing subadditive, f0 equal to 0. Okay, and this function is widely used because dn over 1 plus dn is a bounded metric. Sometimes you want a metric, but you don't want this metric go to infinity. So you use this, you have the original metric, unbounded, and apply this function. You will get a bounded metric. It's a metric function. It defines the same topology, but it's bounded. So that's for some application, you need this property. Okay? And this is easy to understand. Increasing is easy to understand. F00 is understand. Subadditive. What kind of function is a subadditive? Remember that we have the convex function. What is convex functions? If the graph looks like this, it's convex function. But convex function is not subadditive. It's not. We say the concave function. Are subadditive. Concave function is subadditive. How do we get concave function subadditive? So convex, what is convex? You have FA, FB, and you have T, 1 plus T. Add them, you have this point. This is A, this is B. This is TFA 1 plus TFB. It is greater than or equal to. Am I right? Yeah, it's a second. Yes, it's a linear combination. It's greater than or equal to f of TA plus 1 minus TB. TA plus 1 minus TB is a point here, so it's lower. The value is lower than this. Convex. Concave is the other way. Concave is the other way. Hold on a second. Okay, so what is a concave function? Concave function is like this. This is A, this is B. So the TFA plus 1 plus 1 minus 1 minus T, 1 minus T, my bad, minus 1 minus TFB is less than or equal to f of TA plus 1 minus TB. Okay, so the graph is above this segment. Okay, concave function, f is concave if and only if negative f is convex. So one is convex, you flip it, it becomes concave. Okay, f is concave and if and only if negative f is convex. They are like the twin concepts. And then we can prove that concave functions are subadditive. Concave functions are subadditive on this 0 infinity, on positive functions. How do we show it? Okay, so let's try to prove it. So first, we have two-step proof. Step 1, so for any x greater than or equal to 0, for any x greater than or equal to 0, and we consider the pair x x and 0. We consider x and 0. Then f tx plus 1 minus t times 0 is ft, which is ftx. Okay, it is greater than or equal to t fx plus 1 minus t f0. Okay, and of course here we assume it's always positive. Because later we are going to compose it with a distance function. So let's choose, and fx is f0 is positive, non-negative. Okay, we added this condition. Okay, and this one is non-negative, so it's greater than or equal to t times fx. Okay, so we are going to add conditions whenever we need. I think this is enough. Okay, so in step 1, what we prove? We prove ftx is greater than or equal to tfx with the condition f0 is greater than or equal to 0. We just directly drop it. All right? Okay, so let's see what we have. We have ftx greater than or equal to tfx. All right? And then for any step 2, for AB in the non-negative part, FA plus FB, then we consider it as A plus B times A over A plus B plus F A plus B times B over A plus B. All right? So we consider this one as T, this one as X. This is T. This is X. This is different T. So we apply the property here. This is always between 0 and 1. A over A plus B is always between 0 and 1. So this is good for T. So it's greater than or equal to A over A plus B times FAB. Here is a B over A plus B times FAB, A plus B. So add them together, it is equal to FA plus B. So what do you get? You get FA plus FB is greater than or equal to F of A plus B. So it's a subadditive. It's a subadditive. All right? So the condition concave plus F0 non-negative will imply subadditive. All right, so that's the condition, and you can check that this function x over 1 plus x is is concave. It is concave. And also remember that in the convex function, we know if the function is differentiable, the derivative is increasing is convex. Of course, here we can say the similar thing. F is differentiable. F prime is decreasing. F is concave. F is concave. You can check that this one has a decreasing derivative. It has decreasing derivative. Okay. Okay, so that's a little argument about the composition between a function with a distance function, a metric function, not distance, metric function. All right. Okay, let's back to the to our problem, the proposition. Let's back to our proposition. Our proposition is about the a matrix space, the Cartesian product Xn with this D. We already showed the first part, it is a matrix space. And second, we are going to show that the convergence in the Cartesian product is a component-wise convergence. Okay, so assume that the distance of cosine k and the cosine approaches 0 as k approaches infinity. Okay, the distance approaches 0. Then we know that for each dn of xkn xn over 1 plus the distance xkn xn, it's just one part. It's less than or equal to 2 to n, the distance of cosine k and the cosine. This inequality comes from the definition of a D. D is an infinite sum, a series. You just remove all the terms except the nth term. You leave the nth term because this is always a positive. So you just leave this positive nth term. Then you do not have equality. The distance is greater than or equal to it. And you move this the denominator 2 to n to the right side. So you have this. Okay, so n is fixed. N is fixed. For each n, it's always fixed. The component, the coordinate is fixed. When k approaches infinity, the distance cosine k and cosine approaches 0. So we have the limit k approaches infinity, the distance between x and k xn over 1 plus dx n k xn, distance is 0. And this implies distance x n k xn is 0. Okay? So we get one direction. We get one direction. If the sequence approaches 0, then each component will approach 0. All right? And second, assume that the dxn k xn approaches 0 as k approaches infinity for each what? For each n greater than or equal to 1. Assume component-wise the sequence converge to the given xn. We want to put them together. The thing is the following. It approaches 0. It means for every epsilon greater than 0, there exists capital K in the natural numbers such that for k greater than or equal to capital K, we have the distance of xn k xn is less than epsilon. The issue is the following. This k depends on this n. For different component, for different coordinate, you have different kn. So this capital K is actually a function of n. But when you consider all of them, you have no idea how to control an infinitely many kn. So if we consider kn for all n, we do not know if we can find a uniform k greater than or equal to kn for all n greater than or equal to 1. Right? Because we need a capital K so that whenever little k is greater than capital K, all these conditions will be satisfied. Right? We cannot do that. Okay, so that's a place this 1/2 enters. So for 1/2, we know that the sequence converges. So there is a capital N in the natural numbers such that sigma n from capital N to infinity 1/2 to nth power. This tail is less than epsilon over 2. Okay, it's less than epsilon over 2. Okay, so this capital N is fixed. This capital N is fixed. It does not depend on k. It has nothing related to k. This N only depends on epsilon. Okay, and then we only consider the first what? First n minus 1 coordinates. You see, that's the place we change from infinitely many coordinates to a finitely many coordinates. Okay? And because of this, we know that there is a k in the natural numbers such that for little k greater than or equal to capital K, the each component dn x kn xn over 1 plus dn x kn xn, this is less than epsilon over n minus 1, capital N minus 1. Let's divide by 2. Alright, so this is epsilon. This n depends on epsilon only. It does not depend on the others. Okay, then when you add them, the distance between psi k psi is sigma n from 1 to infinity 1/2 to power n dn x kn xn over 1 plus dn x kn xn. We're going to break it into 2 parts. We break it into 2 parts. And the tail, because this one is less than 1, this factor, even though it's very complex, it's less than 1 times 1/2 to nth power n from capital N to infinity. So this is less than 1/2 epsilon. The previous part, we know each of them has coefficient 1/2 to nth power. It is less than 1, so it is less than n minus 1 times epsilon over n minus 1. Of course, I add coefficient 2 in the denominator. All right? So put them together, it's less than epsilon. It's less than epsilon. Okay, so this just implies for each epsilon you have a capital N, so that whenever let me see, not capital N, you have a capital K. Yeah, hold on a second. Yeah, you have capital K, my bad. And you have capital K for all epsilon greater than 0. You have a capital N from capital N. There exists capital K such that for all k greater than or equal to capital K, this place, when you have this k greater than capital K, you have this inequality. All right, so this place you need k greater than or equal to capital K. This capital K depend on this capital. Okay, first step, second step, and the third step, you have this. Then the sequence psi k converges to psi as k approaches infinity. Okay, so we prove the back and forth. We prove back and forth. This converse proof, the proof of the converse part, is also an exercise. Try to make this more reasonable. I just gave you the idea how to handle the infinitely many coordinates. Okay, infinite many coordinates is controlled by this convergent sequence, convergent series, and also you need to make sure that this metric is bounded metric. You see here when you use that, it is a bounded metric. Okay, there's the other part. We're going to show that the second part. We show that the x NDN is compact for all n, implies xndn dxnd is compact. Okay, so how do we do that? We have that famous counter diagonalization process. So every time we proceed one coordinate and choose a subsequence. Okay, so what is a counter diagonalization process? We show that every sequence in X has a convergent subsequence. Okay, every sequence in X has a convergent subsequence. How do we do that? So let psi k xkn, n from 1 to infinity. In X, for each k greater than or equal to 1. So we have a sequence, psi k. I have a sequence. And remember, each sequence is just an element in X. So you have a sequence of sequence. So let me write this. We have psi 1 is like x11, x12, x13, x14. Psi 2, x21, x22, x23, x24. Psi 3, x31, x32, x33, x34. Psi k, xk1, xk2, xk3, xk4, and so on. Okay, so we consider the first column. Consider this x11, x21, x31, x41 in x1 in the first coordinate space. x1 is compact. x1 is compact, then the sequence xk1, k from 1 to infinity, has a convergent subsequence. A convergent subsequence. Then, okay, right? For the compact set, every sequence has a convergent subsequence. Okay, then the author gave an argument about the notations. Convergent subsequence, normally we will say, okay, so kj, The subsequence is denoted by kj. But the problem is, when we have kj in the second column, we're going to use kj as the sequence. Then you have a subsequence from kj. You will have, later you will have a kji, and then you will continue. This will, because you will consider column by column, column by column. This is an infinite process. You will have a long, infinite indices, sub-indices. So that's not a good notation. That's what the author says, open a notational Pandora's box. It's horrible, it's bad. So in order to solve this notation problem, we don't use kj as a subsequence. We use a set notation. So let me see what it is. Okay. So assume the sequence xk1. Here k belongs to a subset n1 is a convergent subsequence where n1 is a subset of n. Here is a natural number, set of natural numbers. N1 is just subset of it. It's like K1, K2, K3, they form a subset. Okay? So that's the argument in the first column. And then consider x1k, k in n1, xk2, k2, my bad, second column. In x2 is compact. Then this xk2, k in n1 has a convergent subsequence. Convergent subsequence. This time we called xk2, k in n2, where n2 is a subset of n1. Okay? So every time n2 is subset of n1. So you repeat this in the case coordinate. In the case coordinate, not k, let's nth coordinate. In the nth coordinate, we have xkn. N belongs to n sub n minus 1. You see, second coordinate, first you consider n1 is in xk. Xn is compact. Then xkn, n in n minus 1 has a convergent subsequence. A convergent subsequence is denoted by xkn. K belongs to n. K belongs to n. Right? So for every, therefore, we have what? We have the limit, the xkn, k belongs to n. This is always convergent. Whenever you have n match, it is always convergent. It has a limit, xn. If it's kn minus 1, it may not be convergent, but we have kn for this n. It is always a convergent subsequence. And then we claim, so for every coordinate, this is nth coordinate, you have the convergence stuff. So we claim that psi kj, no, we don't need to claim this. Now, okay, so now it's not this one. We are going to construct a subsequence psi kj from psi. So what is a psi kj from psi? Let kj be the jth integer in nj. So for example, this in a kn, then kj will be the corresponding. For example, if you have a k2, you will find n2 the second integer. Okay, so for example, k10 is the 10th integer in n10. So the diagonal, that's what we call the diagonal. Nth integer, kn, nth integer. Okay, so we're going to show that psi kj converges to psi by showing the xn is the limit of xn kj, kj approaches infinity. If we can show the component-wise this converges to xn, then of course it's correct. The Cartesian product element will converge to psi. Psi here, sorry. Psi k. This is psi k. Here, psi where psi, I forgot to name. Psi is this xn. Psi is this xn. Okay, so what is the process? We first find a subsequence in the first column, a convergent subsequence from first column. It has a limit. It is x1. And in the corresponding position of the second column, you find a subsequence, convergent subsequence. It is called x2. Okay, so for example, assume the first column, only the first, third, fifth, all the odd positions, they form a convergent subsequence. Then they will give you x1. And then for the second column, you only consider the odd positions. In this subsequence, you find a convergent subsequence. You get x2. Then you back to back to the first column. You do not consider all the odd positions. You just consider the corresponding positions. Then still, it is a subsequence of a convergent sequence. It still converges to x1. So by this process, x1 is always the limit of the selected items. Okay? So you go through for the third, fourth, fifth, so on, the columns. You still keep, so by this process, you always keep the convergence for the previous terms. Okay? And this one, this kj, for j is greater than or equal to n, always belong to the nj. No, not nj, nn. not always belong to the Nn. Whenever this J is greater than N, it is always a subset of Nn. Of course, for the subset of Nn, the xnkj, the limit J from 1 to infinity, it's just the previous part. It's a subset, it's a subindex. For the subindex, remember this index is selected so that the corresponding items converges. Okay, so this is a subset of n sub n. All right, so of course this is true. This one is true. Then the psi kj will converge to psi. Okay, so for this problem, I'm not so sure if I make this clear because it's really a little bit scattered. So here, there are several steps, especially this counter diagonalization process. The diagonalization process just help us to guarantee when you move to the next step, you still keep the result from the previous steps. So every time you keep your own, you keep your known result and explore new result. So that's a diagonalization process. All right, and okay, so we stop here for this video, and we will continue in the next video.